that wise, obviously. So, without fear, therefore, we write the vorticity transport equation in two-dimensional flow as what? In two-dimensional flow, we start again. We said d with t is equal to what? Remember, we said we have already gotten this one. Plus what? But this one is what? Is generally what? Zero. Is zero. Is zero. That is what we just proved here. That if the flow is two-dimensional, this eventually is going to be zero. Whatever that this is, because the fact that this one is zero, because this is zero, so because this is zero, it will destroy this, so the whole thing is zero. So this aspect is zero. I didn't want to take it for granted. So without logic, you can quote without any fear that if the flow is two-dimensional, then the rate of transport of vorticity, as you can see here, is what? So is equal to what? Of course, this indeed shows the diffusivity of the vorticity vector. Diffusivity, that is the diffusion, the way diffusivity is diffusing through the fluid. The way it is diffusing through the fluid is established by this for 2D flow. This is generally true for two-dimensional flow. Okay? That reminds me, there's a question I want to ask. You may be asked to prove this at any time, but it's better you go through this. It's very easy that you should show that starting from this result, starting from this, then prove that this is zero for 2D flow. So it's very easy, just state what you have stated there and get result. Very elementary. Okay? So this, of course, is a good approximation, what we said before. But could you still remember what is a streamline? How is it related? Question 1. What is question 2? What is a streamline? How is it related to a stream function? Don't forget, a stream function, you did it. Professor Mrs. Akupelu taught you, and I also taught you a stream function. What is a streamline? I'm not going to answer this. What is a streamline? We call a streamline. A streamline is a line. Some people used to call it an imaginary line. It's a line drawn in a free flow such that every tangent to it is along the velocity of the flow. Of course, then how is it related to a stream function? A stream function is such a function related to a streamline. It's such a function related to a streamline, and it is represented by, of course, in most cases, it still refers to this 2D flow. In 2D flow, a stream one, I've answered that the streamline as imaginary line. Imaginary line or curve. Imaginary line or curve drawn in a fluid. Drawn in a fluid such that every target to it, to the curve, every target to it is parallel to the fluid velocity. Parallel to the fluid velocity. Of course, you know that. You've done it in the class. Just a quick revision of that anyway. So in which case, what are we saying? Is that if, for example, fluid is flowing in this direction, so that's the direction of the fluid flow. That is going to, there are several, I don't pick particular one. There are maybe a particular case. In which case, if at this place a tangent to it must indicate velocity direction, a tangent to it here must indicate velocity direction, and so on. Here, say that's also a tangent to it. At this place is also velocity, so it varies along. But this line itself is called a streamline, and a streamline is denoted by what? Is as a function is this. Since it is a function of x, y, and it must be equated to what? It's equated to a constant. That's a streamline. There are several streamlines. Like streamlines along the wing of an aeroplane, the aerofoil, and many others. Now, a stream function, of course, I've shown it here. So this one is streamline. Streamline is a curve. But if now the function itself, we're able to plot the function itself, that is the stream function. And well, how is it related to velocity? Relationship with velocity. The velocity as component what? Q. It has to component U, V. Because we are working on 2D flow, so we don't need W is 0. So in that wise, therefore, and the relationship is simple. You have done it. We said that U is in terms of what? Yeah, if you differentiate this with respect to Y partially, that's the component of velocity, and V is differentiated partially with respect to what? Respect to X. Of course, the reason why we pick this is that equation of continuity, mass transport, is identically satisfied. If you check quickly, you see that if you take it like this, of course, we cannot change it. This we enable so that by switching, so that continuity equation in what? In 2D is identically satisfied. So you can compare it with Cauchy-Riemann equation under the complex analysis. So what we are saying is you can check if you differentiate U with respect to X, V with respect to Y, of course it will not be 0. Don't just okay, if you differentiate this, that means you are having what? Di X of di psi di Y, which now represents our U, then plus di Y of minus di psi di X. Let us simplify this. Don't jump into conclusion that is 0. So clearly, this is going to be what? Because of this minus what? Di 2. You can write it as di Y di X. But because A string function is a uniform function and it is uniformly continuous. So the order of differentiation is irrelevant because this function itself, psi is a uniform function, uniformly differential function or functional. So therefore, the order of differentiation, don't forget analysis, is irrelevant. That means this is still the same thing as what? Di x, di y. And the answer is what? So obviously, this our statement is justified. That in the case of string function, the equation of continuity is satisfied and it's a well-chosen function. It's well-chosen. Although it depends, it varies with regards to the same line. It's very with regard to several constants because that constant we put, two streamlines can never cross. Two streamlines can never cross. So in that wise, that means from here it follows therefore that our zeta, it has only one component and the only component is along what? So this is di what? Our zeta, which is di u di y, we just drawn it, minus what? I don't develop it. Okay.
Di v di y minus di u di x.
Di v di y, di v di y minus di x. That is it. And if that is the case, if you substitute, what is your v? Something for your v. You can write it in terms of string function. In terms of string function, therefore,
is di v di x.
Di v di x.
Yes. Di v di y.
Di v di x, di u di y. Is that?
Yes, it's correct.
So it's correct. So from this you can see if you substitute for your v, what is v? What is u? Our v is what? So our v is, that is di x, or v. V is minus di psi di x, okay, minus u is what? U is di psi di y, okay. Of course, this can be interpreted as what? As minus of what? Minus of x squared plus what? Di y squared. Okay? So, and clearly, you know, we can write this as minus, well, di x squared plus di y squared of psi. And you can use the Nabla notation. This is the same thing as what? Okay, so without loss of generality, we can just use that to represent that. Okay? So, so in that wise, therefore, we can now write our result as what? Zeta. What is going to be zeta? Zeta squared will now be what? Okay, so if that is the case, what is the our equation now is what? 2D flow. What is transport equation? So, which is what? That is d what? The t is equal to is it? That's what we got. That is generally valid. It is generally valid. Then, what happens if we expanded this? It can be expanded. This expands as used as total derivative plus you still remember that this, of course, stands for total derivative. So we are now equating this to what? We are now equating it to this. Okay? So if you now substitute for this, what will this give you? Who is now going to be substitute? This one is what? You substitute if you substitute for this minus so this is scalar, scalar. This one is scalar. This is also scalar. So the answer is what? Okay, so from here, if the flow is steady, or we can write it as t plus q dot del is equal to this. What happens if the flow is steady? If the flow is steady, you know, steady means anything that goes with time must be what? Must be zero. If the flow is steady. Therefore, you cancel this. For steady flow, what will you be? For steady flow, therefore, we can write it as what? That means we now have q dot theta is equal to what? Is equal to minus, okay, this is also another form of vorticity transport equation in terms of the stream function, and in particular if again if this one is approximately 0. If the right hand side is approximately 0, if Q is 0 approximately, then we obtain what? We obtain biharmonic equation, which is what? Because this one is 0, that means the biharmonic equation is what? 4 psi is equal to 0 for the string function. Psi. I think with this, I think I'm okay for what we have done so far. The only thing that you should be expecting some exercises on this type of problem, which of course I will give you later. Well,